This is part 2 of a series of lectures for section 5.3 in Math 311, a course on linear algebra at Western Illinois University. So, last video we looked at the Gram-Schmidt process. We learned about the Gram-Schmidt process and kind of went over why it works. So this takes any basis of a subspace and replaces it with an orthogonal basis. But it actually does a little bit more. It actually at each step, it actually gives, it actually shows that the first I vectors of this original basis spans the, is the same as the span of the first I vectors of this orthogonal basis. That is, the span of x1 through xi is equal to the span of u1 through ui. Okay, so this is actually a little more powerful, results. So we're going to do we're going to do a calculation here. The calculation is going to get very cumbersome and it's easy to make mistakes. So the important thing is to take your time. So in this example on page 4, we are going to use this process for this basis consisting of these vectors, x1, x2, x3. Now, these are linearly independent, so of course they are a basis of R3. And of course we already know there's no orthogonal basis of R3, namely the standard basis. But we want to use the Gram-Schmidt process because again we're going to we want the corresponding spans of the smaller subspaces to coincide. Okay, so we're going to use this. So U1 then is just going to be x1. That's 1, negative 1, 1. U2 then is going to be x2 minus x2 dot u1 over u1 dot u1 times u1. So this will be 2, 1, 3 minus the dot product of x2 and u1. So this would be 2 minus 1 plus 3. Okay, so that should be 4. And then u1 dot u1 with itself is just 1 squared plus 1 squared plus 1 squared. That's 3. So that's 4/3. 1, negative 1, 1. This is 2 minus 4/3. 1 plus 4/3. And 3 minus 4/3. Okay, and if we do this right, this is 6/3 minus 4/3. That's 2/3. This will be 3/3 plus 4/3. That's 7/3. This is 9/3 minus 4/3. That's 5/3. Okay. So we can replace this with 3 times this vector. So I'm just going to do that, and this will be 2, 7, 5. Okay. So that's going to be our U2. Okay. So we'll say our U2 is actually going to be this vector. All right. All right. So U2 now 2, 7, 5, and we can easily check that this is orthogonal to that. All right, now let's do find what U3 is. U3 is going to be x3. All right, so you want me to write this formula? I guess I should. Okay, so this is x3 minus x3 dot u1 or u1 dot u1 times u1 minus x3 dot u2 over u2 dot u2. Okay. So what will this be? This will be 102. Okay, x3 dot u1, so that's this vector and this vector. So this would be 1 plus 0 plus 2, that's 3, right? And then we already know that u1.u1 is 3. Okay, so this is going to be 3 over 3, 1 minus 1, 1. And then we take x3.u2. So this is going to be, here's u2, this is going to be 2 plus 0 plus 10. So that's 12. So this is going to be 12. And the length of u2 is going to be, that's u2.u2 is going to be 4 plus 49 plus 25. Okay, so that's going to be quite a big number. That's actually 78 when you add everything up. So this will be 12/78 times 275. And this is where the calculations get really ugly. Okay, so you just want to give yourself enough time and work through this. You got a common denominator. We're fortunate that this 3 over 3 is just 1. Okay. What I did is, if you work through this, obviously your common denominator is going to have to be 78, and I get negative 24 over 78, negative 6 over 78, and 18 over 78. And you can multiply everything by 78, and you get negative 24, negative 6, 18. And you could use this if you wanted to, but if you don't notice that 6, and actually negative 6 divides all of these, so we can multiply this by negative 1/6, and what we will get is this will be 4, 1, and negative 3. Okay, we're just going to multiply it. So here we multiply this by 78, and then we multiply this by negative 1/6, and we get this. Okay. And so our orthogonal basis will be 1, negative 1, 1, 2, 7, 5, and 4, 1, negative 3. Okay, and you can check that these are orthogonal. We have 4 minus 1 minus 3, so that's 0. This is going to be 8 plus 7 minus 15, that's 0, right? And we already know these two are orthogonal. So this is an orthogonal basis. Okay. Now, so that's again if it makes you feel any better, I had to redo my calculations quite a bit when I was working this example out. Okay, so because fractions. All right, now the thing here is we can actually go a little bit further. We can actually once we have an orthogonal basis, we're just very close. We're not that far away from finding an orthonormal basis. Remember, an orthonormal basis is a basis where it's orthogonal, but all the vectors have length 1. And so to do that, to get an orthonormal basis, we just have to find the length of each vector and divide by that length. And here, for the lengths, we can see what it will be. This will be 1 squared plus negative 1 squared plus 1 squared. So that's 3. Take the square root. This is going to be the square root of 3. Here it's going to be, you can see this will be the square root of 78. And here this will be 16 plus 1 plus 9. 16 plus 9 is 25, plus 1 is 26. So take the square root of 26. Okay. So to get an orthonormal basis, we divide all the components here by square root 3, divide these components by square root 78, and these by square root 26. So we get 1 over square root 3, negative 1 over square root 3, 1 over square root 3, and so on. And now this becomes an orthonormal basis. Okay, of our subspace. Okay, and then but the nice thing is you can do a lot of nice things with an orthonormal basis that you can't do with an orthogonal basis, and that is going to lead to our QR factorization, and I think we will do that in the next video.